Good morning, everyone. I'm going to discuss about something that's a little bit different than most of the other presentations you probably hear during this canola week. So my presentation is going to focus on the canola protein, using canola protein as a building block for polymer applications, especially in food and non-food industries. I'm Nandika Bandara. I'm an assistant professor and a Canada researcher in food proteins and bioproducts at the University of Manitoba. So why do we need to focus on the polymer applications for protein? So most of you are aware that the protein industry is experiencing a rapid growth, and it's expected that within the next few years, protein growth, the protein processing and protein industry is going to have its increase that we have to keep up with, especially with the other things happening around the protein industry. For example, when the protein ingredient demand goes up, that will open up avenues for some of the co-product and byproduct utilizations. At the same time, when we look at the Canadian context, most of the Canadian provinces, especially the prairies and the British Columbia, we are producing most of these protein crops, especially the prairies. When you look at the canola production, one of the important crops that we discussed today in several presentations, canola is one of the major cash crops produced in the prairies. So there is a specific economic advantage of value adding or the value addition to this particular product or the crop. So most of the protein related research on canola has happened basically on the agronomic practices, how we can improve the agronomic practices, increasing the yield, or developing or breeding better yielding varieties. These are the primary research happened during the past. At the same time, since the canola, the primary focus is on the oil extraction, people started working on improving the oil quality. But right now, there is a huge demand on what we can do for the leftover canola meal. In the beginning, people started using it in animal feeding, but then with the time, people started to understand why we use it in the animal feeding when we can use it for some other high value applications. This is where some of the new research avenues are opening up in terms of canola byproduct utilization. For example, how can we improve the nutritional quality? How can we improve better processing technologies so we can extract protein in a better functional state? At the same time, what kind of value-added opportunities are there that we can explore in order to add more value to the protein fraction leftover, which is going to be leftover after protein extraction? So one of the areas that we are trying to use these canola protein value addition experiments or the research is using it in biopolymer-based food packaging. So why do we need to focus on food packaging? When you look at the plastic industry, especially food industry, we are using a huge amount of plastic annually for the food industry alone. For example, for the food packaging industry, the total use of plastic is around 78 million metric tons. But unfortunately, only 14% of this total plastic is going to be recycled, where others will end up in landfills, inland water sources, or even in the ocean, where you see the environmental pollution happen the most. So plastic-based packaging, they're mainly deriving from the petrochemical refinery byproducts. So there is a question on the sustainability. Can we keep up with the requirement for these plastic-based packaging materials over the time with the producing petrochemical resources? At the same time, with all the concern over environmental pollution and the greenhouse gas emission, can we sustain the petroleum-based product over the time? So this is where the biopolymer-based packaging comes up. So as a biopolymer, we can basically use any of the proteins, fatty acids or lipids, polysaccharides, or even cellulose for these food packaging applications. However, unlike the synthetic polymers, which are derived from the petrochemical industry, for example, I'm showing here the styrene or polystyrene, which is one of the primary food packaging material that's used in the industry, as well as how the polymerization will happen with this, right? So when you look at the polystyrene, for example, in here, when you look at the polystyrene, they are made made up of monomer units. With the monomers, it's easy to do the polymerization because you will get identical polymer unit with similar monomer units inside that. With that identical monomer units, it will give you an advantage mainly because you can have predictable polymer properties. But if you look at amino acid, where the proteins are made of 20 different amino acids. They have different structures, they're not identical, and they will polymerize in side chains as well. So you can't get a really nice, neat monomer unit because you are working with 20 different amino acids with 20 different type of side chains which can be polymerized in a different ways. So you are working with a heterogeneous polymer when you work with protein specifically. Same thing with starch or even with lipids as well. So with that, we have to work around to improve the material properties when it comes to protein-based packaging materials. So one of the new way to improve the material properties, especially when it comes to biopolymers, because mainly due to that heterogeneity I mentioned earlier, biopolymer-based packaging materials generally have poor tensile properties or the strength, poor elasticity. So they are like not that resistant for like deformation. At the same time, their flexibility is not good. Most of the biopolymer-based packaging materials developed in the past are brittle. So with that, we are looking at a new ways to improve that main issues associated with biopolymer-based packaging. So one of the way to do that is using nanomaterials. So there are multi-class nanomaterials that you can use in the research. For example, nanoclay types like bentonite and montmorillonite. Those are some of the things that can be used in order to improve the polymer-based applications. Graphite oxide or the graphene oxide are another class of nanomaterials that you can use. But in our research, we are mainly using nanocrystalline cellulose, especially for this canola protein-based packaging films, because this is another biopolymer. So basically, we are taking cellulose and digest it into get the crystalline regions, which can convert into nanoscale particle with unique functional properties. So all the other nanomaterials can also be used, which we are working as well. But nanocellulose among them is organic or the renewable biopolymer too, which gives a unique advantage. So with that, in our group, we are working on multiple different ways to improve the packaging material properties or the bioplastic properties of canola protein-based films using this nanocrystalline cellulose. It sounds very simple when we talk about adding a nanomaterial into the packaging films, but it's not that simple either. The main reason is the nanomaterials are in like nanoscale. They range from 10 to 150 or 200 nanometer in the size. When you add a nanomaterial into a polymer matrix, they tend to aggregate together, like shown here, instead of properly dispersing in the polymer matrix. This phenomenon, we call it exfoliation, because if you need to get the advantage of a nanomaterial, the nanomaterial need to be exfoliated and make a nanocomposite with the polymer, in this case with canola protein, without having it as an aggregate. So one of the main challenge with adding nanomaterials into protein or in any biopolymer is this aggregation. So with that, we develop a specific method so where we can improve that dispersion of the nanomaterials and exfoliate nanomaterials in the protein matrix, so where we can get a packaging film with improved functionality. When you're looking at here, this is actually a packaging film developed in our group. And as you can see, when we work with canola protein, that color is there because of the leftover phenolic acids. But in certain packaging applications, this is actually an advantage because there are certain packaging materials where you will need protection from the light. So we can use this brown color packaging material for such applications. So I wouldn't necessarily put it as a disadvantage when it comes to the canola protein. But the biggest challenge is in mechanical properties, especially the poor mechanical properties and poor water barrier properties, which is required in packaging film. So we work with the nanocellulose to improve the film properties. One of the primary ways that we used to improve the exfoliation as well as the material properties of the nanocellulose to avoid that aggregation and reducing the material properties is the oxidation of nanocellulose. So we use a method called tempo-mediated oxidation, where basically, like I'm not going to go into the chemistry of the tempo oxidation, but what we basically did was converting the hydroxyl group or the alcohol groups present in the nanocellulose structure into carboxylic group. So what it does is when you increase the amount of carboxylic groups on the nanocellulose surface instead of hydroxyl groups, it will increase the repulsion between individual nanocrystalline cellulose strands, which help because when you put it in the polymer matrix, in this case in the canola polymer, it will help to disperse it properly, or we call it exfoliate it properly in the canola polymer matrix. So again, I'm not going to go into specific details about the method that we use for the oxidation of the nanocrystalline cellulose, but we basically use sonication to disperse the nanocellulose first, and then work with sodium bromide as a catalyst and sodium oxychloride to maintain the that catalytic reaction, and then we modify the nanocellulose to do the oxidation that we wanted. After the oxidation, we dialyze it, remove all the leftover chemicals, and then use that pure or like the purified nanocellulose, modified nanocellulose for our experiments. After that, we use the method called solution casting for film formation at this stage, because we're working at the lab scale to test out the possibility of nanomaterials. And this is actually one of my students making the packaging films and then taking it out. So this is the casted film after that. So once the film casting is done, one of the primary things is we need to characterize their film properties. So there are three main mechanical properties that we need to look at. One of them is the tensile strength. The other one is tensile or elastic modulus. And the third property is elongation and break. With the tensile strength, as you can see in here, you can see that compared to the control canola film, which is basically about the canola protein without any nanomaterials, either modified nanomaterial, tempo modified or unmodified nanomaterial, your tensile strength is around like 3 megapascal for the packaging film. That's the unmodified canola film. We did add cinnamaldehyde because we wanted to check the possibility of making antimicrobial film at a later stage. But when we add the essential oils, if the mechanical properties are decreasing, then that's a disadvantage. So we didn't focus on the antimicrobial properties, but we add the cinnamaldehydes as an additive just to see whether there is any impact on the mechanical properties. But with the addition of the cinnamaldehyde, there is an increase in the tensile strength, almost up to 4 megapascal. With the unmodified nanocellulose, as you can see in here, you can increase the mechanical properties from 3 megapascal all the way up to like 6 megapascal when you add nanocellulose at 3% weight by weight of protein. The important part is when you add, let's say, 5% modified nanocellulose, your tensile strength goes all the way up to like 7 megapascal. If you add it, like let's say 5% cinnamaldehyde with 5% nanocellulose with 1% cinnamaldehyde, you can increase that tensile strength almost up to 9 megapascal. So compared to that control, where they only had 3 megapascal strength, the new film with 5% nanocellulose, modified, like tempo modified nanocellulose, now you're talking about 9 megapascal strength. This is a significant enhancement of the material strength. When we talk about the tensile modulus or the stiffness of the material, because when we apply a force into plastic, if it deforms, if it's not resistant to that deformation, then it's not good enough for the packaging material. Again, I'm not going to go into like all of them, but as you can see in here, like compared to the control where there is an elastic modulus of roughly around 50 megapascal, once you add 5% tempo modified nanocellulose, you can increase that elastic modulus almost up to 200 megapascal. So that's a very good improvement in terms of the stiffness of the material. The other important thing is about the elongation and break. This is something that we normally observe with all the canola protein-based films. When we increase the amount of nanomaterials, they normally tend to reduce the elongation and break, but still, compared to the control, it's better at 5%. But if you work with, let's say, 3% nanocellulose, there is a significant improvement of the elongation and break as well. Water vapor permeability, compared to the control sample, there is a slight reduction, but not too much with the tempo modification. So that's why we did another modification at a later stage to improve the water vapor permeability as well. So this is how the packaging films would look like at different nanomaterial addition levels, as well as the scanning electron microscope showing the surface roughness, especially at like tempo modified nanomaterials. At 3%, you can see that there's smooth surface on the material. The other thing is we look at the protein structural changes as well. So with the tempo modified nanomaterial addition, we did observe a protein structural changes at the secondary structure level, where we see a reduction in the beta sheets and increase in the unordered structure. This is something that we observed in our previous research on canola protein-based adhesives as well, where there is an increase in the unordered structure due to nanomaterial-induced protein denaturations. We did the X-ray diffraction to identify the exfoliation of the nanomaterials. So I'm not going to go into too much detail about it, but what we basically observed with the X-ray diffraction is the exfoliation of nanomaterials pretty good, almost up to 5% in the tempo modified nanomaterials, but unmodified nanomaterials, when it comes to 5% level, there is a slight aggregation of the nanomaterials, but after you modify it, it's much better in terms of the exfoliation. We did manage to improve the surface hydrophobicity of the nanomaterials with the addition of nanomaterials, as you can see in here, because we measured it through the contact angle. This is something that's very important when it comes to packaging film. So having that better hydrophobicity will help in better water barrier properties. We did look at the thermal properties of this one as well. And in terms of the thermal properties, we managed to improve the thermal properties of the packaging films as evidenced by the thermogravimetric analysis when we add the nanomaterials. This is something consistent with the literature as well. So in terms of the summary, especially with the tempo modified oxidation, we managed to improve the material properties of canola protein-based films. I'm going to go into the other experiment very quickly with the time limitation, just to show you like what we are doing right now, because as I mentioned earlier, the water barrier properties were not great when it comes to the tempo modified extractions. So what we did was we grafted oleic acid into nanocellulose, a hydrophobic long chain hydrocarbon fatty acid, in order to further improve the hydrophobicity of the materials. With that, we did the FTIR to recognize the chemical interaction between the chemical and molecular interaction of oleic acid with nanocrystalline cellulose, which we confirmed with the FTIR. And then we look at the mechanical properties. So as you can see in here, even with that, with the oleic acid based modification, we managed to improve the tensile strength. At the same time, we managed to improve the elastic modulus as well as the elongation and break. What most important is about the water vapor permeability of these films, because especially with the oleic acid modification that we did, as you can see here, we could manage to reduce the water vapor permeability significantly compared to the films. So it looks like grafting a hydrophobic polymer in terms of the water vapor permeability is much more effective in developing a packaging film compared to a modification like tempo mediated oxidation. So we are still working on the full characterization of this work, but this is what I basically want to discuss at this point. And last but not least, I quickly wanted to thank all my funding agencies who are supporting for this one, especially my Canberra Research Chair grant, NSERC Discovery Grant, MITAC's Canada Foundation for Innovation, as well as the New Frontier Research Fund, and especially the University of Manitoba and Dalhousie University. And I'm hoping to do a during the panel discussion, I'm happy to answer any of the questions that you wanted me to answer. And thank you very much and have a nice day.